तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Today's lecture we are going to again look at some examples of polynomial interpolation, as we would look at some of the implementation of Newton's form which we saw yesterday. We will just start with that, and then we look at the implementation of the Newton's form for equally spaced data, and then we look at the Lagrange form of the polynomial, the implementation, and then we would go on to looking at the error in these polynomials. So, to start with, we revise what we did in the last few classes. That is the nth order polynomial. We said that in the Newton's form we can write in this fashion, that is, this is a polynomial which would pass through x0, x1, x2 up to xn minus 1. So, this nth order polynomial with the coefficients of this polynomial, which these coefficients we saw can be obtained by looking at the divided difference method, where we had tabulated the values at x0, x1, x2, x3, x4, etc. as f0, f1, f2, f3, f4, and then we computed the divided differences, and we stored those divided differences into the same functions values, the function array f0, f1, f2, f3, f4. We saw that in the program that I could create an array called x and f, okay, these arrays, okay, and then I could store these values of x and f in this values in this array, and so that is 0 to 3 in this x and x values, and 0 to 3 f going from 0 to 3 for the y values, that is the function values. And then what we did was we computed the divided differences, that is fi minus 1 for different levels. Here as j was indicating the whether it is the first divided difference or the second divided difference, etc. So, we start with j equal to 0, that will be the first divided difference, and then we had fi minus 1 divided by xi minus xi minus 1. So, that is basically computing these quantities, right, f1 minus f0 divided by x1 minus x0, f2 minus f1 divided by x2 minus x1, etc. So, that gives us these divided differences. And then what we did yesterday was to say that these values can be stored in the function itself. Okay, so that's what we did here. So the function takes this function at this divided differences were stored into these function values. The reason being that in the polynomial construction we need only f0, fx0, x1, fx0, x1, x2, fx0, x1, x2, x3. We need only these as the coefficients of the polynomial, and so when I compute these divided differences here, these num values, okay, I could start storing this set of values into these 4 array elements, and the next set of values, this 3 could be stored in these 3 elements, and these 2 in these 2 elements, and the last one, which is not shown here, will be stored in this number. So that is exactly what we did yesterday, okay. And then we could print out that, and then once you have the coefficients in this form as f0, fx0, x1, fx0, x1, x2, etc., we could compute the polynomial by using a nested form, and that is what is shown here. Right. So, I start with f of 0, remember, so now you remember f of 0, f of 1, f of 2 and f of 3 are the coefficients of the polynomial, which are the the function at 0, the first divided difference at 1 and the second divided difference and the third divided difference, and these are the coefficients. And then I will write this in the nested form. You can see the nested form here. So, you have x1 minus x0 and a bracket starting here, okay, and this bracket would be closing only at the end. You can see this matching brackets, it will close only at the end, okay, and then this x1 minus x0 multiplies f of 1, okay, and then you have x1 minus this x minus x1, x1 here, this x1 is the value at which we are evaluating the polynomial. So, x minus x1 that multiplies now another bracket starting here, which again closes only at the end, okay, into f2 plus x minus x2 into f3. So, that is a nested form which we discussed in a few classes ago, okay, and then we can evaluate these functions at various values of x1. That is what we have done, and then we could plot this function, which also we did. So, we could plot this function and we could get this function values in various forms. Okay, we will just okay. So, this what we want to do is we want to write down these functions, and we are doing exactly for this set of values. Okay. So, the 2.5, 3.75, 5.0, 6.25, and these are the function values here, and we are having a polynomial which interpolates through these points. Okay, that is what we wanted to show. Okay, so we can see this being plotted here, okay, this function values, and what you see here as this square blocks here are the values tabulated at 2.5, 3.75, 5 and 6.25, and this symbol, see this round symbols here, these symbols are the interpolated values, and you can see that it actually goes through this polynomial very well. So, it does not matter what the axis here is, what we have to see is that this interpolated polynomial actually goes through these set of points which we have mentioned here. Okay. So, the square being the function values given to us, and the round symbols being the interpolated values, and then they go through that. Okay, so, that is what we saw this. Okay. So, we could also look at other problems which we will look at a little while later in using other methods. When we compare different polynomials, we would use these functions also to compare them. Okay. So, we could for example take a functional form and evaluate this function between 1 and 8 for example, okay, and construct a set of discrete points, and then construct a polynomial which goes through that. That tells us something about the error in our interpolating polynomial. Okay. That will be a useful thing to learn. Now, look at the same Newton's form, but now with equal intervals. Okay. Remember this form of the polynomial, it is again Newton's form, but for the data is evaluated at, or the data we have is tabulated at equal intervals of x. Okay. So, S here is actually xs is a point at which we want to evaluate the polynomial, xs minus x0 divided by h, where h is the spacing between the data points. So, the s written here is xs, xs is the point at which we want to evaluate, minus x0, x0 is the first data point which we have tabulated, divided by h, where h is delta x given. Okay, that is the distance between the 2 tabulated values, and that's same for all values. Okay. So it's unlike the previous case where we had 2.75, 3.75, 5, 6.25. Okay. So this is, so we could have it. Okay. Here also we actually have equally spaced, but we didn't use that. Okay. So this, for example, this is a good example of that. So 3.75 minus 2.5, 1.25, 1.25, etc. So we could use the same data to actually use the same data and actually use this functional form of the polynomial and obtain a polynomial and then compare that. So we will see that in this here. So that functional form. So we call that as equal space. See, so this is a program which would implement that particular quantity. Again, we have, let's say, set of an array which is x and the function f. Okay, we store them in this array. Okay, so here what I have done is I have taken that log x program, okay, the log x function, okay, and I created this function. So I'm going back and doing this this particular problem using equal space data. Okay, this particular problem, that is, I take log x function, okay, log to the base 10x, okay, and I evaluate that function between 1 and 8 in some set of discrete intervals, okay, and then I would get an interpolating polynomial through that. Okay, so I just create this set of discrete points at equal intervals h, where h I choose to be 0.5. Okay, so I evaluate between 1 and 3 in this case. Okay, between 1 and 3, I evaluated a certain number of at every point x equal to 0.5. Okay, and then I have a set of x of i's, xi's, and f of i's. Okay, xi's and fi's. So this will be the tabulated value then. Okay, so then I am writing this in this particular thing onto the screen, the xi and fi values. Okay, and then I would go and construct that divider difference. So here it is the same as the Newton's form, as I said. So we will use the same divided difference method, no difference. The only change being that in the earlier case, in the Newton's method, when we had a set of discrete points, okay, we had them at arbitrary intervals, and we were arbitrary intervals, the divided differences were made as f of I plus 1 minus f of I, or f of I minus f of I minus 1, divided by x of I minus x of I minus 1. Okay, we have to divide it by the spacing of the data. But since here it is all equally spaced, okay, as we saw, all that the spacing, that delta x, that is xi plus 1 minus xi, is absorbed into this function here. Okay, and we write that s as xs minus x0 into h. So delta f0 here is simply, we remember, is f of I minus f of I plus 1. Okay, so that is for the evenly spaced data. Okay, sorry. So we will have just only delta f of I minus f of I minus 1, and these are further differences of the divided difference, that is the second order difference and the third order difference, etc. So that is what exactly we are doing here. So again we have, like in the Newton's polynomial case, starting with j equal to 0. Okay. So remember, all these points are exactly the same. Once we have constructed the function here, the discrete set of points from this function log x, we have constructed a discrete set of points x of I and f of I. Okay, and then this part of the program, starting from here, is exactly the same as what is in the previous case of Newton's polynomial, except that the divided difference, we don't divide this fi minus fi minus 1 by the interval that xi minus xi minus 1. But instead of that, we just simply construct the divided differences as the difference between the function values. Okay. Again, so let's start with j equal to 0. That's the first divided differences, and I will go from 1 to n. I will go to 1 to n since j is 0 in steps of 1. Okay, and we store the first function value at j equal to 0 in the df1. Okay, and then we construct df, that is df as the difference between 1 and 0, f of 1 and f of 0, and then we go back, and since this is I greater than 1, this line is executed only at I greater than 1. So we go back here. So we go to I equal to 2, and we come back here, and the one which we computed, the value which we computed as f of 1 minus f of 0 is now stored into df1. So, remember df1 is now f of 1 minus f of 0, and then we go to the next line where we compute now, since I is 2, f of 2 minus f of 1, and then we store this value which was f of 1 minus f of 0 into f of, now f of 1, j is 0. So, if this is now 1, I is 2 and j is 0. So, I minus 1 is 1. So, f of 1 now stores the first divisor difference, that is f of 1 minus f of 0 into that, and we continue the loop, and the next f of 3 minus f of 2 will be stored in f of 2, and f of 4 minus f of 5 minus f of 4 will be stored in f of 4, etc. So, we'll use just like what we did earlier. Okay, we just store all the divisor differences into the function f, and then we change j value. Okay, now we go to j to 1, that is the second divisor difference, and because we have stored all the first divisor differences into the function, now we don't have to worry, we just have to take the difference between the f's again. Right. So, that is the advantage. So, I would show you this graph, this plot again. So, this is exactly the same as this. So, now all these distances are equal between x0, x1, x2, x3, x4. Okay. So, what we did again was computing the difference between these functions, okay, and storing them, computing the difference between these functions which are f x0, x1, x1, x2, x2, x3, x3, x4, and storing them in f1, f2, f3, f4. That is what we have done in the j equal to 0 loop just now. Okay. Now, we are going to change j equal to 1. Okay. When you change j equal to 1, again we would continue the same thing, that is j equal to 1, I equal to 1. Okay, and I equal to 1, we will compute now f of now 2, j is 1. So, f of 2 minus f of 1, that is what you are going to compute. That is taking f of 2 minus f of 1, okay, which is, since f of 1 had this and f of 2 had this, it is actually taking f of x1, x2 minus f of x0, x1, which is nothing but f of x0, x1, x2, right. So, that is again being stored in this value here. So, in the second loop, I equal to 2, we come back here and stored. Now, I equal to 2, we will compute. Remember, when I equal to 2, we store this f of 2 minus f of 1 into df1 and compute f of 3 minus f of 2. Right now, j is 1, I is 2, so this is 2. J is 1, I is 2, so this is 3. So, this is f of 3 minus f of 2. Okay. And then we come to the next step and store the one which we computed as f of 2 minus f of 1 into f of 2. Okay. That is I is 2, j is 1. So, f of 2 is what it is. So, we will store it in this value. Okay. So, that is saying that this function now has gone into f of 2, and the next difference will go, that is this will go into f of 3, etc. Okay. So, we will compute exactly the same thing. So, we get all the divisor differences at the end again as f1, f0, f1, f2, f3, f4. So, we get f0, f1, f2, f3, f4 as the divided differences, and then we can use the nested form again, like in the Newton's form. So, the only difference again so far between the equally spaced data and the unequal spaced data in the Newton's form is the construction of the divided difference, where we will not divide the function by xi minus xi plus 1 minus xi. Okay, that is the only difference. Okay, and then we have the nested form again in this form. So, now this is the nested form is slightly different. Okay, now we are coming to next nested form. Okay, the nested form here is slightly different because it is this form which we are going to use. Okay, so because this functions now involves the value at which we have to evaluate the polynomial. Right? So, in that sense, it is slightly different. Since now the coefficients of the polynomial now has to be evaluated at every value we want to get it. That is, we have to get this s value computed at every. So, this s values has to be computed at every point where we want to evaluate the polynomial. Okay. So, we have just completed the calculation of delta f0, del square f0, del cube f0, del n f0, but these s's has to be computed at every point, because it is xs minus x0 by h, where xs is the value at which we want to evaluate the polynomial. So, that is what is done here. You can see that. we can see that S, now we were going to evaluate the polynomial starting from 1 to 3, okay, at intervals of 0.2. Okay. We have tabulated values at the intervals of 0.5, but we want the polynomial in the in between intervals. So, we are going to evaluate that at intervals of 0.2. Okay. So, S is, as I said, the x, now x s in this thing is now x1 here. So, x1 minus x0 by h is your S. Right. So, as x1 changes, S also changes. Okay. And then we would say that the function value, we will start with the first term. Okay. The first term is okay, the first term is just f of 0. As you can see, the first term is just f of 0, and the second term is s into delta f0, that is f of 1, right. So, that is f of 1 is my delta f0, f of 2, because I remember I stored these things into my function value. So, this is my f of 1, and this is my f of 2, and this is f of 3, etc. Okay, that is what is been done here. Okay. So, you start with f0 plus this value, that is s into, so we have just chosen our y value, okay, to be start with this, that is s times f of, so okay, f of n by n. Okay, that is what you are going to do, okay, here, and then we are going to go backwards. Okay. So, what we do is we are going to start from here, okay, and then we go backwards and complete that. So, our n in this particular case is equal to, we will be having 4 points, we have 7 points, so it will be n equal to 6, let us say. Okay. So, we will start from that value. So, first we start with the n, the last term here. Okay. So, we will take f of n. Remember, this is f of 1, f of 2, f of 3, and this is f of n. Okay. So, we start with the last value, and that has to be divided by n factorial. Okay. So, that is what we have to do. Okay. So, now this is going to be, remember, n factorial is 1 into 2 into 3 up to n. Okay. Now, I am going to do this in a nested loop. Okay. So, I am going to take out, I am going to make this n. Okay. Now, this gets multiplied. So, I take only s minus n plus 1 divided by n, and that gets multiplied by s minus n plus 2 divided by n minus 1, etc., as it go further. Okay. That is what the loop here is. Okay. This is a nested loop, but we start from the highest order term. So, s into n minus 1, that is s minus n plus 1 into f of n by n, that is the first value which we are taking, which is exactly the same as this one which we are taking. Okay. So, s minus n plus 1 by n instead of n factorial into the f of n, that is what this is. Okay. So, that is to start with, and then I run a loop starting from n minus 2 to 0, j equal to n minus 2 to 0, and then go step by step, dividing it each time, adding to that function the next f value, that is f n minus 1. So, j is n minus 2, so I add to this value here f n minus 2 and divided by n minus 1. Right, I just divide by n minus 1. Remember, this was divided by n, and the next is n minus 1. So, since I have this in the bracket, this function also gets divided by n minus 1. So, it is already n into n minus 1. So, by the time I complete this loop, I have n factorial for the first term, n minus 1 factorial for the second term, n minus 2 factorial for the third term, etc. And the last, I just sum of the function to f of 0, that is this term. Okay. So, that will give me the full value, and I just print it out into a file here called equal.dat. Okay. So, that is what this program is. Okay. So, to summarize this program, I have taken the logx function. Okay. I taken the logx function and then I have tabulated it from 1 to 3 and intervals of 0.5. Okay. And then I wrote that I stored that into a file, into an array of x of I and f of I. And then I used that for f of I to compute my divided differences without dividing it by x of I minus x of I minus 1, because it is equally spaced. And then I use a nested loop to compute, once I have the divided differences, I use a nested loop to compute my polynomial at different values starting from 1 to 3 at intervals of 0.2. And I wrote that into a file here called equal.dat. So, I opened a file here and I wrote that into a file and I closed the file here. Okay, that is a program for computing this thing. Okay, now we will go back, we will go and just run this program and then see what do we get. Okay, so we will run this program. We need a math library there. Okay, so that's, and then we would run this program. Okay, so that's the values at which I have tabulated this this thing. Okay, so I have tabulated it at 1, it values at 1, 1.52, 2.53, etc. So this is the values at which I tabulated the function. So I had 1, 2, 3, 4, 5 data points starting from 0 to 4. Okay, so that's the function value at this points, and this is the, these are the divided differences I got, the coefficients basically of the polynomial, that is delta f0, del square f, del 2 f0, del 3 f0, etc. are also listed here as 0.176, 0.0511 minus 0.023, etc. These are the coefficients, and then I would just now run a program with this. I just plot those data, the data points. Okay, now this is the data points plotted. Again, the line which you can see here, is the log x function. Okay, that's a function which we had. Okay, and this square symbols here are these square symbols are the interpolated values, and you can see that the interpolated value actually goes over the function quite well. Okay, so our interpolation works pretty well. Okay. So we should see, so we saw now two different methods of doing this. So one is using the divided difference Newton's formula, and this is the Newton-Gregory formula in which we have equally spaced data. Okay. So the difference being that the way which we would implement this, implement the nested loop is slightly different. Okay. In this case, we would start from the bottom, okay, and then we would go up to this value. We are computing S for every value which you want to evaluate. In the case of in the Newton's form, we don't need that. We actually have the, once you have the polynomial, the functions, we can simply evaluate the function once for every value of x. So it's a slightly different nested form. Otherwise, it's all this, it's similar. Okay, and again the divided differences are computed only by taking the difference between the function and the divided difference, or the difference between the first divided differences, etc. Yes, that's a form of this. Okay, so now we will look at the next form. Okay, that is the Lagrange interpolation formula. Okay, we again see an implementation of this Lagrange interpolation formula now, and we said that in this case it's been represented by Fn of x here. Okay, we said that this can be written as I going from 0 to n Li, some operator Li x here into f of xi. Now this function Li of x is of order n all the time. Okay, so that is what which we saw. Okay, so if you write it for just the first order term, okay, it would be simply given by this. So Li of x, remember, is a product going from j equal to 0 to n of x minus xj divided by xi minus xj. We saw a derivation of that in the last class, and so we can, this product is runs over all the values from j equal to 0 to n except for j equal to I. Okay, so if you have n, this is n plus 1 quantities, okay, and then so n plus 1 minus 1, so either n products, n terms here. So for n equal to 1, it's just 1, that is, so let's say you have a polynomial n equal to 1 that is going through x0 and x1, okay, and then you will have x minus x1 by x0 minus x1 as the first term, okay, and the second term would be x minus x0 divided by x1 minus x0 as the second term. And you can see that at x1, Okay, f of x equal like x equal to x1, this will give me the f of x1, and x equal to x0, this will give me f of x0. So that's the basic idea of the Lagrange interpolation thing. Formula is that every term is a function value at that I. Okay, so that is if I write it as f of xi. Okay, so now this is the second term. The second term means second order term. Second order term would be x minus x1 into x minus x2 by x0 minus x1 to x0 minus x2, and it continues up to 2. So there will be 3 terms in this. Each of them is a second order polynomial. Okay. So in the case it is n equal to 2, each of them is a second order polynomial. In the case of n equal to 1, each of the terms which is first order polynomial. Okay. And now if n equal to 3, there will be 4 terms. Each of them would be a third order polynomial, etc. Okay. And the idea being that each term would give me the function value, each Li of x into f of x will give me a function value at that I. Okay. So that's the whole idea of this thing. Okay. So we have to again go back and then look at the implementation of this particular formula in this. Okay. That's what we will now see. Okay, so here is a program which would implement this new formula, that is the Lagrange formula, that is saying that the function value is equal to f of I, the function is at any value at any point x is equal to Li of x into f of xi, I going from 0 to n. Okay, so now you remember this, Li go from 0 to n, Li of x and f of xi. So if you have a polynomial which goes through n, let us say 3, n equal to 3, let us say 3 points or 4 points, that is an example which you are going to see, is it goes through 4 points, and then there will be 5 terms in this, right? It goes from 0 to n, okay, the 0 to 4 it will go, okay, there will be 5 terms in this formula, okay, and each of them Li being given by this product xi minus x minus xj divided by xi minus xj for j going from 0 to n, but j is not equal to I. Okay, that is the implementation which we are going to see. So what we have to see is the polynomial as Li of x into f of xi. Okay. Sum over I, Li of x and f of xi, I going from 0 to n. That is what we want to see, the implementation of that. Okay, so we again have the program here with 2 arrays x of 0 and x and f, okay, where x is the tabulated values. We are using the same data points that we done before, okay, and then f of 0. So that is f 0, 1, 2, 3. That is the function values tabulated. Okay, so that's what we have. The function value is tabulated. That is n is 3 in this particular case. And then so now we are going to store the result from this into a data file called Lagrange.dat. Okay, that's what we are going to do. Okay. And again we are going to evaluate this polynomial at starting from x of 0 to x of n in steps of 0.1. That's what we want to do. And again, so this is now a slightly different implementation, right? So it's not a nested form or something like that. Okay, now the point here is that for every x value at which we want to evaluate the polynomial, we have to compute this product, right? Okay, so every x value for every I, okay, we have to compute this product, okay, because this product is different for every x value. So we cannot evaluate a set of coefficients and then compute the polynomial at every x, but we have to actually compute the polynomial at every x value. So it looks difficult, but it's as we see in the program, it's much more easier to implement in this particular case. That's what we see here. So we want to evaluate it at, let's say, x1 equal to x of 0, or if we're going to x of some value x1, okay, starting from x of 0 to x of n in steps of 0.1. So we start with y for every x value. We start with the function value is finally going to be written into y. So we start with y equal to 0, and then we say that we go from I equal to 0 to n. So that is we have to do this as you remember that the function value is sigma I Li of x into fi of x, right, or f of xi. So sigma I Li of x f of xi is the value which you want to actually finally obtain. So that I loop goes from 0 to n as we saw it in steps of 1. Okay, and then we want to compute the product. So the product is actually finally will come out as df, which I initialized as 1. Okay, and then I do the j loop here. So the j loop is this one. So I want to evaluate this product. So I just first put it as 1, and I go from j equal to 0 to n, okay, except for j equal to I, and I multiply x minus xj divided by xi minus xj, where x is the value at which we want to evaluate. So it's very simple to implement. Okay, so the x1 is the value at which we want to evaluate. So x1 minus xj divided by xi minus xj is the product. Okay, so for all j values except j equal to I. This notation is j not equal to I. So some programming detail here, j not equal to I is, so if j not equal to I, so this loop is executed only when j is not equal to I. Okay, otherwise j goes from 0 to n, and I initialize this function to 1 value, and now I get the product here xi minus x0 divided by xi minus x0, x1 minus x0 divided by x1 minus x0, x1 minus x0, and then so if I start with I equal to 0, okay, and j equal to 0 is not executed because j is equal to I, so j starts from 1. So I will get x1 minus x0 divided by x1 minus x0, and then x1 minus x0 divided by x2 minus x0, x0 minus x2, etc. So all j values. Okay, so you get all the product. Okay, so and then I multiply that product by the function value at I. Okay, and then I run from I go to 0 to 1, and then I have the final function y. So that's a sum. So the sum is here, the product is here. Okay, so first evaluate the product. So that gets me the Li of x. Okay, and then I take the sum multiplying the Li of x with the f of I, okay, and I sum it up here. Okay, and then I get the function value at that x1, and I write it into the file here. Okay, that's a file. So I can do this. Okay, so I put it into Lagrange.dat, and we just plot that again and then see. Okay, so here is sorry, this is slightly different. We'll just compute this now. Okay, so that was the one which, remember, data.dat was where we stored the function value, the tabulated values, and this is the function values. Okay, so again the green points here, the green squares which you can see here, are the tabulated values, and this the round points are the interpolated values, and you can see that it goes through this very well, and you can see that it is the same as, it gives the same accuracy or same result as what we got from the Newton polynomials. There is no difference between these two. So we see that we can actually evaluate polynomials, we can get the function values, we can interpolate a given set of tabulated values using, now we saw 3 different methods, for equally spaced data 1 and for unequally spaced data 2 methods, that is we saw the Newton's method and the Lagrange's method. Okay. So now does it mean that if you give me any interpolated any set of discrete function, then I can evaluate this function anywhere? Okay. So is that possible all the time? So that's the question which we would ask, and we will find that this is not always true. There will be always an error in the polynomial, and that's something which I can demonstrate here to you. Okay. So I will show you this in a program that. Okay, so here is a program. It's similar to again using the Lagrange's method, but I am using another set of data points here. Okay, so I use another set of data points which is tabulated in this toInter.data kind of this data file. Okay, which is actually something which we have it here. I will show you the data file. Okay, so I want to interpolate this particular set of data. Okay, so I have this data file here. Okay, and I want to write an interpolating polynomial to get the values in between this. Okay, so this is something which we can try. So I have entered this set of this into a file. Okay, so that file is, I call it as toInter.data. Okay, so this file contains all this tabulated values, okay, of x and f of x. And what does this program do? This program first read that file. Okay, so again I want to show you here a way to read the files of. Okay, so I want to read this file. So I have used this fscanf function, okay, to read that file. So first I open that file called toInter.data, okay, and then I go from and I read that file using the fscanf. Okay, I said that while so it reads it line by line till it finds the end of file statement there. Okay. So every file will have an end of file character. Okay, so till it finds the end of file character, it will keep reading. So this while loop here closes at this point. Okay, so this is a while loop. Okay, so this while loop has only one function to be one statement to be executed, that is to scan this file called fp1, where fp1 is the toInter.data. Okay, so that's how you open a file, and you could just read that off, and while reading it also counts the number of lines. Okay, that is I done it by the I equal to 0. Okay, there is other ways of getting the number of lines in a data file, but this is a very simple way of doing it. I equal to 0, we've initiated it, and I'm just scanning that thing till it finds the end of file character, and I increment I at every time. And then after I read this file, I close the file. Okay, it overcounts it by 2. Okay, so I just set my number of data points as I minus 2. Okay, so that's because it starts from 1, it's counting, and so I just wanted to set it by 2. Okay, so that's my number of data file, the data points which I have. Okay, and in this file toInter.data. So then I use a Lagrange's. After that, okay, I have the data in now x of I and f of I. Okay, remember when you use the scanf function, you are given ampersand sign here. And when you are reading, okay, you are pointing it to that addresses and storing the data files in these addresses to which this is pointing to. X of I and f of I is the arrays which I have to store the x value and the f values. And once I have that, I use exactly the same as the one before, the Lagrange's form, okay, and I use the Lagrange's form to evaluate the function, okay, to evaluate the polynomial. Okay. And I am running it from x of 0 to x of n, okay, at steps of point 1. Okay. So I have a set of data points here, okay, and I construct a Lagrange's form polynomial with this, okay, and I evaluate the function values, the polynomial values in between this, starting from this to this in steps of point 1. That's what I am doing. Okay, so that's what we would see here. Okay. So and then this part is exactly the same as what we saw before, that we had y value, and we had the product here, that is evaluating the L of I, the Li of x, Li of x1, and multiplying it by f of xi and doing the sum here. Okay, and the values I got, I am storing it into this thing called Lagrange.dat again. Okay, so we will see this. We will run this program and then see what do we get. Okay, so now I have to run this program. So I run this program. Okay, so That is the data points which we have just tabulated here. I just put it here again. Okay, so now that is the value which we are getting here. Okay, so now you can see. Okay, so now this again the squares. Okay, the squares here are the function values which is given to me. Okay, the squares are the function values which is given to me, and the dot this circular the points are the interpolated values. Okay. And you can see that wherever the circular points were close to the square points, I have a good agreement. Okay, where it is. Okay, but it's quite ambiguous when it is away from that. Okay, for example, this line decided to go down and then go up, and here, for example, it's going up quite a bit and then coming down. Okay. So we are not very sure that whether these is actually, for example, here it decides to go down and then go up this point. Okay. So it's not very clear to us in the initial stage. You can see that when the curve starts, look at the square disk, the square points and the circular disk. Okay, they agree very well at the first point because it's exactly the same value. So function value and the polynomial agrees wherever they are close or they are exactly the same. Okay, so they agree, and the next point it varies a lot. Okay, so given this set of square points, it's not clear to us that this line shown by this circular disks is a good representation. Okay, so that's what I wanted to show you. Right? So it's not clear that the polynomial which we got is the correct polynomial. Okay, or what is the error in this? Okay, there is some error, and what is the error in this? And that's what we want to quantify, and that's what we will look at in the next part. Given a polynomial Pn of x, okay, so of degree n, and we have which interpolates between 0 and n with a function value, okay, tabulated function value x. Okay, now the actual value of the function should be, of course, f of x, right? So f of x is the actual value of the function at any point x. Let's say this is a function, and this function is tabulated at x0 up to xn, and we have constructed a polynomial Pn of x. And we are constructed in such a way, as we just saw in this particular example, that we are constructed in such a way that this Pn of x, or the nth order polynomial, agrees completely with f of x at these points. Okay. So now if x is any point which is different from x0, x1, x2, xn, then what is the error? Okay, so we can define the error as f of x, the actual value of the function, which we don't know, of course, okay, minus Pn of x. Okay. So that will be the error. Right? So f of x is something which we don't know, because x has been tabulated, f of x has been tabulated only for a discrete set of points. So that is x0 to xn, okay? And then we have f of x here, okay, and f of x minus the polynomial value at that x. This we know, okay. And now this is my error, okay. So now question is, we don't know this exactly, but question is, can we estimate this error? Okay. And so we will use the Lagrange form. The Newton form for doing this analysis here. So let's try to estimate this error. Okay, how different is the Pn of x from f of x? Okay, so that's what we would try to get. Okay, so let's say if Pn of x is a polynomial of degree n plus 1, which interpolates from f of x at x0 to xn, okay, and at x bar. Okay, so that's the idea. Okay, so we will try to do that. As I said, x is a point which is not, which doesn't match with any of this x0 to xn, right? Okay, so now we assume that we know this. Let's take this x as x bar. That's what we've done here. Okay, and we say that we know the function value at this point, f of x bar. Okay, and the polynomial is actually not of the order n; it's the order n plus 1 because it also goes through x bar. Okay, we force it to go through x bar. This x bar is some value between x0 and xn. Okay. So now, since it goes through x0 and xn, and also through x bar, we have n plus 1 So n plus 2 points, right? This is n plus 1 points here, and then x bar, so n plus 2 points. And the polynomial which goes through all of that would be an order degree n plus 1. Okay, so then we have this exact equation that p n plus 1 or x bar is equal to f of x bar, because that's the way p n plus 1 is constructed. Okay. So remember that p n of x was a polynomial which went through n points, n plus 1 points, that is x0 to xn. Okay. And then p n plus 1 is a polynomial which goes through x0 to xn and also through x bar, which is some value of x between x0 and xn. Okay, so we have that polynomial. Okay. So then we can write p n plus 1 of x as, right, so p n of x plus p n of x is the n order polynomial which went through x0 to xn, right. And then we have an additional term. Okay, the last coefficient would be then f of x0 to xn x bar, right. Remember the Newton's form. Okay, so we have f of x0 to xn to x bar, and then a product here that is x minus x0, x minus x1, x minus x2, x minus xn into x minus x bar. Sorry, x minus x2, x minus xn. Up to that it will be there, right. So that's the last term. Okay. So remember, once again, I want to emphasize this point, that is p n of x is a polynomial which went through n plus 1 points x0 to xn, right. And then we added an extra point x bar which is between x0 and xn, and then we constructed an n plus 1th order polynomial which also went through this. Now I want to write this n plus 1th order polynomial as this polynomial plus something. If I want to do that, then what I would get would be this, right. So that is the last term, this is the last point. Okay. This point is somewhere in between, but there is an additional point which you have added. So I have to construct this coefficient which is now f bracket x0, xn and x bar, and it will be multiplied by x minus, this will be the nth order term, right. So n plus 1th order term. Okay, because this is a polynomial of order n, and this is a polynomial order n plus 1, and the n plus 1th order term would then be x minus x0 and x minus x1 to x minus xn. That will be n plus 1th order. And then if I evaluate this polynomial at x bar, that will be exactly the same as f of x bar, okay, because we are forced to go through that, right. So f of x bar is p n plus 1 of x bar, which is p n of x bar plus this additional term, okay, into x bar minus xj. Okay. So now what do we see? What we wanted to see in the earlier thing was this difference, okay, the difference at x bar, okay, at x equal to x bar. What is the error of the polynomial, nth order polynomial, if I evaluate this polynomial at any value x bar which is between this but not one of this, right. So that is exactly what we are getting here. Okay, so we get that difference as this term. Okay, so what we see is that the error in this polynomial is actually for any function, any value x bar, which is not any of these values, okay, is given by the next term in the polynomial. Okay, so that is, if you given a polynomial of order n plus 1, it's like n plus 2th order polynomial. Okay, so n plus 2th term. Okay, so n plus 2nd term in this. Okay. So the next term in the polynomial is the error. Okay, so error we can get this. Okay, so error in the polynomial would be like the next term. So can we make, now again, we don't know this values at every point. So can we make an estimate of this? Okay, as I said, we don't know f of x bar, right? So we assumed here that we know the f of x bar. Okay, when we write that, I said the f of x bar is p n of x bar. We said that we force the polynomial to go through that point. For that we need to know f of x bar, right? Okay, so otherwise we cannot construct this function here. Okay, so we don't know this f of x bar in reality, but we can see that the error is of this form. Okay, it's like the next term in the polynomial. Okay, so now question is, can we make an estimate of this? Okay, so that's what we should try to see, okay, whether we could make an estimate, and then we could compute some examples of this actually. Okay. So what we used to do is this theorem. Okay, this is called the mean value theorem. Okay, So which says that if there is a function f of x which is defined between a and b, okay, and it's k times differentiable in this interval a and b, okay, okay, and so if x0 to xk are k plus 1 distinct points in a and b, okay, and then there exists a value between this interval a and b, which a and b, okay, such that this function, okay, is equal to the kth derivative of that function at that point divided by k factorial. Now this is a theorem, okay, so I'm not going to give you a proof of this theorem except to show you that in the first order case we can see this very easily, okay, we call the derivative mean value theorem, and we can see this very easily for the first order case. So the statement is again the following. See, what we want to get is an estimate of this quantity, okay, remember we didn't know f of x bar, okay. So unless we know the f of x bar, we can't compute this coefficient going from x0 to xk, right, we cannot compute that coefficient, okay. So we need an estimate, and what it turns out is that this quantity, okay, is equal to the kth derivative divided by k factorial, okay. So we have an estimate of that already, okay, for some value of x, for some value of x between a and b is given by zeta here. Okay, so that's an estimate, right? So we can actually maximize this derivative. So we can actually, since the function is differentiable, okay, in this interval kth time differentiable, so we could actually look at the kth order. We don't know the function actually, but what I'm trying to say is that the estimate tells us that it is the kth derivative. So if you assume the function to be smooth, okay, and differentiable, okay, then we already have an idea about how bad that function, that polynomial would be, or the error in that polynomial at any point would be. It will be of the order the kth derivative divided by k factorial. Okay. So as you see that as the degree of the polynomial increases, it increases pretty fast. Okay, we will continue on this theme again in the next class and look at some details of what is the implications of such a term would be. Okay, so that would be the thing in the next class.